Hey, grade 11. I'm going to go over 3 different questions here throughout the course of this little video, just trying to help you out with some of these Unit 10 questions. The first one here was given to me by one of the students, and it's about a missile that's leaving the surface of the Earth and it's got a velocity, right? And it says, at what distance above the surface of the Earth will the missile have lost half of its kinetic energy? And you've got to make the assumption that half of that kinetic energy is all turning into gravitational potential, right? So I think the first thing to do here, and the best way to start, is to kind of look at what they want us to figure out, because it's quite a lot going on. So we're starting with an object on Earth here. We've got a spaceship or a rocket ship that's just down here, and it's got a velocity. So what does it have? Well, it's got kinetic energy with half mv squared. Now we can calculate its kinetic energy, and we're going to do that, and then we're going to take the whole kinetic energy and we're going to divide it by 2, and that's just for this very specific question here, and we're going to turn that into potential energy. Now, what do we know about potentials? Well, at the surface of the Earth there's a very negative potential. Now we're going to be working that out, and as you go further away, and the closer you get to infinity, there's going to be a point here, and then we get further away, there's this point in infinity where we say that there's a 0 potential energy. So the potential energy never becomes positive. So by going from here up to here, to this height, we'll call it delta H, what we're going to get is we're going to find that we're going to become less negative. So we've gone from a very negative point to a less negative point. Okay, so that's just an overview of what the question's about. Next, we're going to start figuring out how to answer this. Right, so the first thing that we're going to do then for this calculation, we're going to find the kinetic energy. Okay, the kinetic energy, nice and easy for you to do, half mv squared. Well, what I've done here just there is I've converted from kilometers per hour into meters per second, put it into half mv squared, and we're going to find that if we do this calculation just here, we're going to get 8.42 times 10 to the 10 joules. Now that's the total kinetic energy. So remember, in this question it's asking, I think if it's lost half of its kinetic energy, what's going to happen? So we're going to take this value and we're just going to divide it by 2. So we're going to get, so the change in energy is going to be equal to 4.21 times 10 to the 10. Okay, that's joules. Okay, the next step is going to be to find out the potential energy at the surface of the Earth. Now, you can do this a couple of ways. You can say potential energy U is equal to V times M, where M is just the potential. So if we take the potential and times it by the mass, we've got the potential energy of the object at that location. So doing this, we would say that the potential energy is equal to G M upon R. So, well, that's V, and then we're going to multiply it again by the mass of our object. So the large M here is going to be the mass of the Earth, the small m is the mass of our object. Now I've already plonked this into the calculator, and what we can find is that the energy at the surface of the potential energy is 6.05 times 10 to the 11. Sorry, a little quick edit there. Actually, that should be negative, right? So we've got a negative value, which goes back to what we were saying here, where if we look on the bottom left hand side of the page, it's a negative potential, and the further down you go. So we've got minus 0.65 times 10 to 11, and what we're going to do is we're going to add to that the energy that we've got in, so half of the total kinetic energy. So we're going to do this, we're going to say negative 6.05 times 10 to the minus 11 plus, I'll change colours, 4.21 times 10 to the 10. And let me put that into the calculator. Okay, so having done that, we find that it is 5.63 times 10 to the 11. And I've just noticed that should not be a minus up there, and it was just a minus here. Right, what we've got then is we've got a potential energy. Okay, this is our potential energy in joules. All we need to do is we need to substitute this value back into this formula then. So we've got U equals minus G M upon R. We're going to rearrange to find the radius, the distance from the center of the Earth. So we're just going to have minus G M upon U, and if you substitute those numbers in, you should be able to get the correct answer. Now, I think you're given that on community anyway. I'm not going to put it into the calculator, but that's looking like you should have 6847. So I'm taking this, I'm just reading this from Cognitive now. That'd be kilometers, so 6.8 million meters. And you know, obviously, if you want to find the height above the surface of the Earth, then you've got to take the radius of the Earth away from that. One little thing to point out, you know, you might be wondering why we're not just using E equals mgh. Okay, and the reason we can't use E equals mgh here is because this G is not constant. Now, if we're doing, you know, if we're lifting an object 3-4 meters or 100 meters from the surface of the Earth, then the change in the gravitational constant is so tiny that we don't need to accommodate for that. In this case, though, we're going quite a significant height above the surface of the Earth, which means G is going to be different. So this accommodates for that change in gravity. And it might be that there are some questions that ask you to find kind of, well, what's the difference if we do the proper calculation compared to the assumption that we've just made here? How does that work out? All right, so that's the first question. We're going to go on to the next two just now. Hey, right, so for this next question, I think it's important to know where they're starting from. So it says that an equation for the velocity of an orbiting object is given. What would be the simplified equation for the velocity of an electron? Right, so we'll come back to that in 2 seconds. First of all, we need to start thinking about circular motion and the force between two objects. So we can say that F, the force, is equal to big G mm upon r squared. And our formula, general formula for centripetal force, there's a few of these, but you know, we've got mv squared upon r is going to be really good for this one because we want to find velocity, and that's shown just there. If we equate these, then we can say that g m upon r squared is equal to mv squared upon r. We're going to do some cancelling out, get rid of these m's, get rid of these r's, and then we've got v squared is equal to g m upon r. And of course, if we root the whole thing, that's going to be our formula. Right, so how does this relate to our question? Well, that's what they did for an object orbiting a large body. Now let's think about this for an electron. So the force in this case is going to be K, Q1, Q2 upon r squared, and the other centripetal force, it's going to become a little bit more complicated because this remains as mv squared upon r. And we're going to equate these two then. So we've got K. Sorry, we don't have K. Oh yeah, no, we're doing sorry. K Q1 Q2 upon R squared is equal to mv squared upon R. And there's not as much to rearrange for here to get rid of, so we're going to cancel out that R, and then we're just going to rearrange to make V the subject. So V is equal, or V squared is equal to K Q Q upon M R, and we've just moved that M down, and of course, you know, we're going to be rooting this in a moment. I'm just going to go back to the question now. So the only other thing in here is it says, what would be the simplified equation for the velocity of an electron orbiting nucleus with n protons b? So we can think of this formula now. If we want to make the attractive force stronger, there's going to be n neutrons in there. And I think if we take a look at your options, I can't remember your options exactly. I think they want it in the form of V is equal to the root of what is essentially a constant multiplied by that n upon R. Right, and this is R here. So what's that constant K? I use the terrible thing for the constant there. So this is a constant, and I should not have used K because K is already a constant in this. So let's have V is equal to the root of our actual K, which I think is Boltzmann's constant, K Q Q upon M, all multiplied by n over R. Now if you do the mathematics and you put this in, let's see, we've got, so we're going to take this up here and we're going to say, well, 8.99 times 10 to the 9 multiplied by the fundamental charge squared, 1.6 times 10 to the minus 19 squared, and divide that all by the mass on an electron, 9.11 times 10 to the minus 31 kilograms. If we do that, so that's just taking, remember, that's just taking this section here, that gives us V is equal to square root of something, whatever that was, and we'll put that in a moment, divided by R. And if we do the mathematics here, then we find it's 252.5. So kind of a difficult question, really. I think it's not so easy, but that's what you should find your final answer to be. This final question here should be somewhat of a quick one. If we remember, let's just get some extra information in there. So if we've got a negative charge, then we've got our electric field lines coming in like this, you know, and these are uniform around the point charge. If we've got a positive charge, well then that is going to be similar but with the arrows pointing in the opposite direction. Now note that this question is not asking for the electric field lines. What this question is asking for is the equipotential lines, and this is something that we looked at right at the start of Unit 10. If we look closer to the centre of this positive charge, then what we can see is that there's a lot of flux lines there, and the further we get away from this central point, the weaker it becomes. So just like one of the maps that shows the gradient of heights by having these equipotential lines, what we'd expect to find is if we've got a positive charge in the middle, then our equipotential lines start close to the object, start close to the charge, and then as we get away, they get a little bit larger. And this is something you should be able to find in Cognity 10.1, close to the start of that unit. If not even in, this might be in some other units as well. I can't really think right now. But yeah, so if you're looking for your answer for this one, that's what your equipotential lines look like. So the key factors being that, you know, they're closer together the closer you are to the charge, and as you get further away from the charge, the lines get increasingly distant. Alright, hopefully that helped. Hopefully you're all doing well, grade 11. I know it's stressful times at the moment. Keep it up. Thank you for asking me these questions. It's much appreciated, you know. Gives me an idea of what you're wanting to work on and improve. And it allows me to know that you're actually working. Right, bye.